We are going to have a look at the multivariable regression analysis. We are going to concentrate on drawing and inference, how our inferences. Remember, we have already dealt with the problem of inference in the case of a two-variable regression model. So when I talk about a multivariable regression model, it is simply an extension of the two-variable case. The basic logic behind inference and hypothesis testing in this case is very similar to that of a two-variable case. So once again, like we had said in the two-variable regression model case, if we are happy with just estimating a sample regression function, which is as close as possible to the population regression function, then all the assumptions of the CLRM model are more than enough. But if our objective is not just to estimate but also use this model for further prediction or forecasting, another important assumption should come into play. That assumption is the normality of the error term UI, or normality of the disturbance term UI. We assume that UI follows a normal distribution with mean 0 and variance sigma square. Similar to the two-variable case, even in a multivariable regression model, this assumption of normality of the disturbance or the error term ensures that our OLS estimators, beta 1 hat, beta 2 hat, beta 3 hat, are not just the best unbiased estimators in the entire class of linear estimators, but even among linear and non-linear estimators. So they're not just blue, they're in fact BUE, the best, or they have the least variance in the entire class of unbiased estimators. Since the estimators beta 1 hat, beta 2 hat, beta 3 hat in our three-variable model are all linear functions of the error term or the disturbance term UI hat, the assumption of normality of the disturbance term ensures that these OLS estimators are also normally distributed. The mean of these estimators will be the true population parameters beta 1, beta 2, beta 3. Remember, we are saying that these are unbiased estimators. The meaning of an unbiased estimator is that the mean of the estimator, say beta 1, when calculated for several samples from the same population, will be equal to the actual true population parameter beta 1. Similarly, when you take several samples from the same population and you estimate beta 2 hat, the mean of the beta 2 hat values for several samples will be equal to the population parameter beta 2. That is what the term unbiased means. So when we say that beta 1 hat, beta 2 hat and beta 3 hat are normally distributed, they are distributed with means equal to the true population parameter, and their standard errors or the variances, the formula of the variances have been discussed in earlier video lectures, so you can just look at the formula. Similarly, the ratio of variances, that is sample variance to population variance, will follow a chi-square distribution with n minus 3 degrees of freedom. This is in the case of a 3-variable regression model. Right, so n minus 3 times the ratio of sigma hat squared to sigma squared will follow chi-square distribution with n minus 3 degrees of freedom. This can always be generalized to a k-variable regression model. Similarly, the t-statistic, which can be calculated as per the formula given below, will follow a t-distribution with n minus 3 degrees of freedom. Again, when you generalize this to k-variable regression, we will say that the t-statistics calculated in this manner will follow t-distribution with n minus k degrees of freedom. Remember, n is the total number of observations in the sample and k is the total number of estimators, OLS estimators estimated via the regression function. The t-statistic calculated in this manner in the formula shown in the previous slide can be used for establishing confidence intervals, that is, establishing the interval estimate of the true population beta values, as well as for testing statistical hypothesis about the true population partial regression coefficients. Right? This is exactly similar to how we established the interval estimates in the 2-variable case. So I'm not going into too much detail. Similarly, even for the statistical hypothesis testing regarding the variances, the population variance, the true population variance, you can use the chi-square distribution. Now, when we come to hypothesis testing, there is a slight difference between the simple or the simplest 2-variable case and the multivariable regression model. What is the difference? The difference is in terms of the variety or different types of hypothesis that testing that can happen. So like what we have shown below are the different forms that hypothesis testing can take place. I'm reading it in order. The one type of hypothesis testing is to test the hypothesis about individual partial regression coefficients. That is, if you want to test a hypothesis whether beta 2, the true population beta 2 is equal to a certain value, you can use this regression model's values and test hypothesis regarding that. Another type of hypothesis testing that you can do is to test for the overall significance of the estimated value. Technically, that means to find out if all the partial regression coefficients, that is beta 1, beta 2, beta 3 and so on to beta k, are simultaneously equal to 0. So you're basically testing whether the model that you have specified is significant or is actually correct. Another type of hypothesis testing is to test if 2 or more coefficients are equal to each other. So you have a 3-variable regression model and you want to see if beta 2 is equal to beta 3. And you will test that by using the values estimated of beta 2 hat and beta 3 hat. Another type of hypothesis testing that is possible is to test whether the partial regression coefficients satisfy certain restrictions. What kind of example can I talk about? If you talk about the consumption function, okay, so you are talking about Keynesian consumption function. So you're saying that the consumption level is mainly being determined by the variable called income, right, for the economy, national income of the economy. But also there are some other variables which you consider important. So let's say you're regressing income levels and or maybe per capita income levels and wealth of the society on consumption expenditure. So now we know that the coefficient that comes for the national income level, that is beta 2, will be what we talk in economics, the marginal propensity to consume. So you might want to check whether, as Keynes said, this marginal propensity to consume is actually lies between 0 and 1. So that would be an example of checking or testing whether a particular partial regression coefficient satisfies particular restrictions. Another type would be testing that the estimated regression model is stable over time excuse me, or across different cross-sectional units. So you could see if your regression model, which was estimated in the 1950s in the case of consumption function, holds true or is stable across over the years, and also true in 2000, the year 2000, a gap of 50 years later. And finally, you can test whether the functional form of the regression is correct or wrong, try to get an idea about that. So my plan now is to use an example from the Damodar Gujarati book, Basic Econometrics. If you check the Moodle site, I had once uploaded the 5th edition, the link to get the 5th edition of Basic Econometrics. So I'm going to use one of the numerical examples that is used in this book, so that if you have any doubts in what I'm explaining, you can go back to the book, or if you have any doubts from the book, you can come back to this lecture. So this is the example from the Basic Econometrics by Damodar Gujarati that I was talking about. It is a 3-variable regression model where they looked at the effect of per capita GNP as well as female literacy rate on child mortality. So as soon as you read this sentence, you should be able to recognize that the y variable is child mortality, and there are 2 x variables or independent variables, which are per capita GNP, it's denoted as PGNP in this model, and the second is FLR or female literacy rates. Okay, so this regression result that is shown in the table is based on a sample of 64 units. They have used the eViews package. We can discuss the different types of softwares and different softwares available, both free and paid, later on. But so we had a sample of 64 units. We had data regarding these 3 variables from these 64 units, on these 64 units, and we ran the OLS regression, and this is the result that we got. Once again, our y variable is child mortality, 263.6416 is the intercept OLS estimator for the intercept, beta 1 hat, minus 0.0056 is the coefficient of the explanatory variable PGNP, that is per capita GNP, and minus 2.2316 is my beta 3 hat, that is coefficient for the variable female literacy rate. So the very first line gives you the estimated values of beta 1, beta 2, beta 3, right? They are estimates based on the sample, that is why they are denoted as beta 1 hat, beta 2 hat, beta 3 hat. Okay. One more second. If there is no error term, then this is why I had. The second line just below the estimator values are the standard errors of these OLS estimators. Again, the formula used is the same that we saw in a couple of lectures ago. Below that is the t value which has been calculated for testing that the true population value beta 1 is equal to 0, or the true population value beta 2 equal to 0, and in the third case the true population value beta 3 is equal to 0. So when you assume the null hypothesis as equal to 0, your basic t statistic will be, in the case of beta 1 hat, minus 0, since the true population beta 1 has been, we are testing against null hypothesis is beta 1 equal to 0, divided by standard error of beta 1 hat. So it's basically 263.6416 divided by 11.5932. You can always look it up in a calculator. Similarly, the second t value minus 2.8187 has been calculated based on the null hypothesis that the true population value beta 2 is equal to 0. So if that is the case, the test statistic will be the estimated beta 2 hat minus what has been specified in the null, that beta 2 equal to 0, divided by standard error of beta 2 hat. So here also you will get your t statistic here is calculated as beta 2 hat divided by the standard error of beta 2 hat, and that is the value that is given to you as in the brackets minus 2.8187. Third case, the third t value, we are testing the null hypothesis that beta 3, population beta 3 is equal to 0. So the t statistic will be beta 3 hat minus the value of the parameter given in the null hypothesis divided by standard error of beta 3 hat. Right? So these are the formulas which are giving you the t values in the third row. Finally, the last row shows you the p values of each of these calculated t statistic. Remember, the p value is the exact level of significance at which you can reject the exact and the lowest value of significance at which you can reject the null hypothesis that beta 1 equal to 0 or beta 2 equal to 0 or beta 3 equal to 0. So once again, to recollect from the earlier lectures, you can either assume that your alpha level of significance at 5%, 10% or 1% for that matter, and accept or reject your null hypothesis, or you can decide to choose on the basis of the p-value. Most commonly used method is that you fix both. You fix your alpha level of significance, say at 5%. You look at what the p-value is. If your p-value is lesser than 5%, then you decide to reject the null hypothesis and you say that the coefficient, estimated coefficient, is significant. Or so if my alpha level of significance is 5%, in terms of numbers I will always say 5% is 0.05. okay, so since the p-value of beta 1 hat is 0.00000, it's far less than 0.05, you will say that beta 1 hat is significant at 5% level of significance. Okay, significant means that we are rejecting the null hypothesis. What is the null hypothesis? That beta 1 is equal to 0. So if you reject the null hypothesis, that means beta 1 is statistically significantly different from 0. And if it is different from 0, it means that it has some valuable impact or effect on the value of yi. Similarly, if you look at the p-value of beta 2 hat, it is 0.0065. Given that alpha level of significance is say 5%, that means 0.05, and your p-value that is quoted for beta 2 hat is lesser than 5% level of significance. It is lesser than 0.05. So once again, if your p-value is lesser than the alpha that you have chosen, you can reject the null hypothesis. What was my null hypothesis? That beta 2 is equal to 0. So I am rejecting that null hypothesis, which means beta 2 is significantly different from 0. And if it is different from 0, what does that mean? It implies that the variable PGNP, per capita GNP, has a strong impact or influence on my y variable child mortality. Finally, having a look at beta 3 hat's p-value is 0.0000. So it's a very small value, and your alpha, chosen alpha level, if it is 5%, again 0.05 is much greater than the p-value. So you will see at 5% level of significance, the null hypothesis cannot be accepted. The null hypothesis was that the population beta 3 is equal to 0. So if you cannot accept the null hypothesis, that means beta 3 is significantly different from 0, and hence I am saying that the variable female literacy rate has a statistically significant impact or influence on y variable child mortality. So things to remember: when you reject the null hypothesis, or when you say that we cannot accept the null hypothesis, you are saying that the coefficient that you're talking about in the null hypothesis is significant. This is basically, this usage comes from the fact that generally the null hypothesis is something equal to 0, the coefficient equal to 0. And when you reject that null hypothesis, that means if it's different from 0, that means it has some sort of influence on the y variable, which is why we say that the variable associated with this coefficient is significant. It has a strong influence on the y variable.